Yeah, so I thank the organizers for giving me the opportunity to talk. And I'll be talking about ZZ instantons in 2D string theory. So let's cover some preliminaries. So string theory, as you all know, is the study of strings propagating in a space-time. And strings propagating, as you probably already know through pop science, that strings propagating in a space-time traverse 2D surfaces. And hence, the quantum theory of strings naturally involves the studying of embedding of these 2D surfaces, which will be which are Riemann surfaces in a particular formulation called the world sheet formulation of string theory. So it involves embedding, studying the embedding of such surfaces in the space-time. And since Riemann surfaces are classified through their genus, the correlators in string theory have a natural genus expansion, where this G is the genus, and GS is the string coupling. Now, in world sheet formulation of string theory, we use free bosons to describe these space-time dimensions. So these x mu's are like functions of the world sheet coordinates on a 2D surface, and these describe the directions in the space-time. So hence we have an embedding of these surfaces in the space-time. So here you see a sphere, a torus, and a sphere with two handles. These all are getting embedded in space-time through these free bosons. Next part of the preliminaries, open string theory. So since now we want to, so that was for the closed string theories. So we had closed Riemann surfaces. Now we want to study the open string theories. We have to have surfaces with boundaries. So yeah, so open string theory naturally involves studying embedding of Riemann surfaces with boundaries in some space-time. And now the natural question is, what are the possible boundary conditions? So for the free boson, we have either Dirichlet or Neumann boundary conditions. And this leads to possibility of some non-perturbative objects in the space-time called D-branes. So this is also a popular statement that people discuss whenever discussing D-branes, is that these are the objects on which the open strings, end of the open string, map to. Or yeah, it's better phrased here actually, objects on which open strings end. So you have a Riemann surface with boundary. So here is an example of D-brane. So this red object, so consider a two-dimensional space-time. So along x1, I have a Dirichlet boundary condition. So it is fixed. So, and along x0, I have a Neumann boundary condition. So it's extended along that direction. So that's why D-branes are characterized by the space-time dimensions in which there is the Neumann boundary condition. So these are the open strings I'm talking about. So they end on this red object, and this characterizes my D-brane. Yeah, and these are some examples of world sheet with boundaries. The most basic one, disk, then comes the annulus, and then comes the disk with two holes or torus with one hole. And a general diagram in this setting is proportional to string coupling to the negative of Euler characteristic chi. And that's why you have these scalings with the string coupling. And you can imagine them being embedded in space-time like this. So this annulus, this boundary is getting mapped to this particular point in the space-time, x1, because you have a Dirichlet boundary condition along x, and this particular boundary getting mapped to this other point. And similarly, you can have two boundaries getting mapped to a single D-brane as well, so which is shown here. Next, open closed string theory. So upshot of the previous slide is that in open closed string theory, you will have correlators whose general expansion will look like this. So in the beginning, there will be that perturbative series I showed in the first slide, which corresponds to the closed string theory sector, you can say. And then comes then comes a series which is suppressed in 1 by GS, because as GS becomes small, this e to the minus C by GS, this doesn't have a good Taylor expansion. So it's non-perturbatively disconnected from this series. Because yeah, it all comes down to the fact that such effects don't have a good small GS expansion. So yeah, and in this above expression, this C corresponds to the disk partition function or the D-brane tension, or if you have a D-brane, there will be a corresponding tension, or people call it D-brane mass as well. But yeah, so if so the other series will be suppressed. So the C character quantifies the suppression we have of this other series. So this C is related to that. Now comes the important point. So this series can only contribute if your C is finite. And this C is finite only for the case of D-instantons. What do I mean by that? In all directions of space-time, you have Dirichlet boundary condition. And or when we have compact Neumann directions. If I have a non-compact Neumann direction, this C will be infinite, and hence that series won't contribute. So only possibility of having such corrections is through D-instantons, or when you have compact Neumann directions. Yeah. And so after C, the subleading piece is this N I have written here. This is the normalization. This is a number. So this N comes from this exponentiated annulus. And this is e to the minus C by GS I have written here. So a general diagram expansion is like this. You have a closed string expansion, and then you have other non-perturbative sectors here. Some boundary condition corresponding to some particular D-brane, some other D-brane, which just amounts to saying some boundary condition or some other boundary condition. So now comes the main point. So we will be working in a setting of 2D string theory, and the analog of D-instantons here will be ZZ-instantons, as I will explain. So usually in consistent string theory, you must have heard that we need 26 dimensions or 10 dimensions. However, it's still possible to get consistent string theories called the non-critical string theories where we don't require these critical number of free bosons or space-time directions. So one such example is 2D string theory, in which we have a simple free boson as like the other space-time directions, but we have a weird boson Liouville field which has a non-trivial potential, some exponential potential. And of course, there are these ghosts which are not relevant right now. But roughly, you can think of it as an X-phi space-time, as I've shown here, X-phi target space. So for experts, if they like, it's like, so in Liouville CFT, I put some special parameter values so that the ghost anomaly is cancelled and we get a consistent string theory. Now, the relevant boundary conditions for these Liouville field, for X, I have defined earlier, Neumann or Dirichlet. For the relevant boundary condition to get a finite C, the instanton action I showed in the previous slide, are the ZZ boundary conditions devised by Zamolodchikov brothers in 2001. And these are localized at phi goes to infinity. So they are like roughly like Dirichlet boundary condition localized in space-time, like D-instantons. But they are labeled by some positive integers, Mn. So now we further considered a compactified boson, where I have this, Ashok talked about it in the morning, that you have this X identified. And now we have both Neumann and Dirichlet leads to finite instanton action. Now the object of interest, exponentiated annulus I showed earlier, that corresponds to such a calculation where this Z is like the annulus partition function. And it is typically divergent as t goes to 0 in this integral. However, the string field theory interpretation of this exponentiated annulus helps us to deal with this divergence. And this is the replacement rule devised by Ashok in these references a few years back. And this replacement rule basically helps us to make sense of this integral even when we have these terms in this z of t, e to the minus 2 pi h1t for h1, h2 negative. The main issue comes when these are 0, and these are called the 0 modes, and these have to be interpreted appropriately in the string field theory setup to deal with these. So at generic radius, we have only one bosonic 0 mode. The bosonic 0 mode corresponds to translations along the circle, the compactification circle. And the fermionic 0 modes have some interpretation in terms of U1 gauge fixing, which is probably not important right now. But I'll just tell you, this is again a replacement rule given by Ashok. The case of interest for me was R equal 1, where I have, along with this 0 mode corresponding to the translation along the circle, I have 2 more 0 modes. So I have 3 bosonic 0 modes. this leads to some enhanced gauge symmetry, probably not relevant. But the thing is that these extra 2 bosonic zero modes can also be countered by the same method devised by Ashok earlier for the translation zero mode I told you about. So yeah, so one of the interesting results I can tell you is the exponentiated annulus corresponding to the, so okay, I probably skipped it, but at r equal 1, the r equal 1 case, what happens is this boundary conditions are not Dirichlet or Neumann anymore. They are parameterized by SU2 group, and that makes a big difference. But if I use the same regularization procedure I told you, like this and the replacement rule in the previous slide, I end up with the result that I end up with the results which match with the dual formulation called the matrix quantum mechanics formulation of the 2D string theory. And one of the interesting results is this, that when you have unequal boundary conditions for the annulus, the exponentiated annulus is just trivial. And this works also for the case of generic R when I have, say, Dirichlet on one boundary condition, one boundary, and Neumann on the other boundary. So yeah, we can further check these disk 2-point annulus 1-point functions as well. And this is inspired for this R equal 1 case, which was already done in other similar cases of minimal string theory in these references. Yeah, and yeah, I can skip this, maybe just come to discussion. So one thing I didn't tell you was why were we interested in R equal 1 case? It was because there exists 0+0 matrix models, 0+0 dimensional. So there is no space, no time, just a simple matrix integral, as opposed to 0+1 dimensional MQM dual, which serve as toy model for the complicated examples of so-called gauge gravity dualities. So this dual with 2D string theory is a toy model to study gauge gravity dualities, and we are studying non-perturbative aspects of that. So that's why it was important for us. Now, yeah, and another reason is because duality with the 0+0 dimensional matrix integral doesn't require double scaling limit. And one peculiar feature is that this duality requires this analytic continuation of matrix dimension to purely imaginary number. And this is the exact reason why matrix model free energy develops non-perturbative corrections. So yeah, I'll take questions.
My question was basically about the motivation. I think you said something about it in the discussion. So what kind of physics do you really miss if you don't take these non-perturbative corrections into account?
Like tunneling to a different saddle. If you look in this MQM theory, MQM description, which reduces to some free fermions in a inverted Gaussian. So you have a fermions filling a C on the one side of the potential. All the excitations there are captured by the perturbative series, first series. But when a fermion crosses this potential and goes, that is not captured by the first series I mentioned. So this series won't capture that. You need these.
You need the non-perturbative part in the string theory, or do you need it in the matrix model as well?
Like from matrix model, we know what it is. Okay. But on string theory, it corresponds to D-Instanton. That's the statement. Yeah. So it's always like you are tunneling from one saddle to other. And this is captured by such configurations in string theory.
Let's thank Rishabh for the wonderful talk.